Thanks for joining. I also wanted to take the opportunity to thank Francois and Doyen and INET for hosting me for the last few months. I'm very grateful to be able to spend some time here, and it's been very productive, and I hope we can continue the collaboration into the future. So that's good. For people who don't know me, I'm Glenn. I'm working mostly on production networks and the role of firm and household or consumer heterogeneity in both micro and macro outcomes. And this paper is part of that agenda or project. Actually, it's super early. This is the very first time we're presenting this. I'm presenting this. So I started writing slides 2 days ago. So it's super preliminary. It's incomplete, but I think this is exactly the right audience to pitch the idea to, and so we're very much looking forward to your comments and suggestions on this. It's joint work with Vasco, who is at Cambridge, Stephen, who has been at Oxford and is now at UCL, and Yabra, who just started his PhD in computer science in Zurich. So let's start with a question to you guys, actually. What is a market? And I'm not saying what's the physical location of, let's say, a flea market, but as an economist, how should we, or how do we tend to define markets? No wrong answers.
Trading platform.
Trading platform, good.
As a trade economy, I think of countries as markets, or
Okay, good.
or regional trade agreement.
Okay,
Right.
good. It's interesting. We should ask this as an exam question to students, but
The prices gone crazy.
okay, yes, that's a good idea.
Matching algorithm.
Matching algorithm, okay, good. Any other thoughts? So I went looking for this, and so going back to Adam Smith up to the most recent competition policy committee report for the OECD, there seems to be over the last few hundred years some differences, but there's a common thread to these things. And so Adam Smith says something about the forces of supply and demand that matter. Prices set determined through competition, maybe the role of competition, market power, imperfect competition, and most recently, competitive constraints a firm faces, i.e. demand supply side substitution. So while the definition has become a little more technical, but these are kind of stable things over the last few hundred years. However, what is competition? How do we think about competition? What substitution? What are forces of supply and demand? These are multi-dimensional objects, and as Paula and others have been saying, you think about these things in many different dimensions. What things matter to define a market? And so, just to highlight a few which matter in reality, there might be geographical dispersion. So some markets might be very local, and others might be very national. So let's take the example of I'm a local bakery here in Oxford. My competition is going to be probably other bakeries here in Oxford in walking distance. It's not going to be any independent baker down in London. Okay. On the other side of the spectrum, we have national markets. And so think of telecom. They are competing in a national market at the national level and servicing those national markets. The second dimension might be product space.
And of course, it's
Sorry.
international.
Yeah. So sorry. Yeah.
Indeed,
Yes.
all the levels.
Yeah. So geographical concentration, dispersion, delineation. Yes. Another dimension might be product space. Very often as economists, we think if we can define something that's an homogeneous product, then it's easier to think about competition. And that's kind of the whole baseline of industrial organization, right? So cereals. Do we care about cereals? Maybe not perhaps in the aggregate, but this is a clear, well-defined, differentiated or homogeneous market where we can think about competition. Same for ready-mix concrete. Quality is important. Suppose there are two suppliers of white t-shirts, and one guy is supplying 100% cotton white t-shirts, and the other guy is supplying 100% polyester t-shirts. High quality, low quality. Who's competing with whom? Maybe only the high quality guys compete with each other. Maybe they're competing with each other as well. And so these things are kind of unclear unless you're able or willing to make assumptions on how firms are going to interact in the market. So this is just to show that not all of what we think is competition aligns with what we mostly do when we take these things to the data, which is saying, here's a NACE code, here's a sector, an ISIC or a NACE code. This is the competition. We're going to calculate market shares. We're going to calculate concentration. this market is concentrated versus a non-concentrated market. Going back to the idea of me being the local baker here in Oxford, this is, I mean, you put all the bakers in England together, in the UK together, and say these are competing, right? It's surely not the case. Big firms, we know they're multi-product firms. They account for a large fraction of aggregate output. They're producing multiple products and or services, and even across multiple high-level industries. So if you look at very big firms in manufacturing, they're often doing manufacturing services, financials, and everything, right? So these are very big corporations, which you'll never be able to capture with their main NACE code. And so 5-digit sectors, what we have in Belgium is the most granular information about sectors. You cannot capture this kind of information about geography, quality, or product space in that sense. On the other side of the spectrum, you have the people who are doing competition policy. So I know a little bit more about the EU than the US in this case. But so they say, we're not stupid, we're going to think about what's a relevant market. And so that's a starting point of anything that's competition policy oriented. What's a market? If I know the market, I'm going to calculate market shares. If this market share is above a particular threshold, we're going to call this firm dominant. If it's abusing its dominant position, we have this article that's going to make sure you're walking between the lines. We can think about merger control. All these things actually matter, and they're based on defining a relevant market. However, how they think about defining a relevant market is based on very little information. So, for instance, almost tongue-in-cheek, but not really, it's like if there is a particular firm that's under scrutiny, they will go to this firm and ask, what are you producing? What are your sales of every product or service? Who are your competitors? We go to those competitors. What are you producing? What are your sales? What are you doing, right? So they try to map this market based on that. Of course, you see a lot of issues with that, right? First, it's qualitative. Second, there's a lot of incentives to misreport about that. I mean, think of Google. If they go to an antitrust case, they say, we are just a very small provider in a large landscape of digital services, right? So that's kind of the framing that's going on there. Yeah. So identifying a market is critical for any kind of quantitative analysis, both in macro and micro. So there's this nascent literature or rising literature on the observed rise in market concentration, superstar firms, and all these things, but they start by defining concentration. Concentration is defined based on market shares. You need to think about what are the markets they are competing in. Micro, so as I highlighted, competition policy, you have a dominant position from the moment you have 40% market share. Below that, you're not even on the radar mostly. Above that, we're going to see whether you're playing by the rules, and then we can see if we're going to address those issues. Trade, very often, we think about intra-industry things. So we try to shy away from everything that's cross-sectoral. We're thinking about the most famous workhorse model in trade is intra-industry productivity. It's a millet, right? So we think about TFP estimation. TFP estimation is the productivity of a firm relative to its peers. And that's very often a 2-digit NACE code. Industrial organization, as I mentioned, people have been getting their careers on identifying a particular market that says, with cereals, we can think about this. We can think about ready-mix concrete, we can think about coffee or cars. So in this paper, we would like to identify relevant markets that reflect effective competition, so true competition without looking at assumptions and then putting those assumptions on the model and the data to back things out. In geographical and product space, and not based on sectors. And so for that, we're going to use comprehensive information on observed firm-to-firm supply and demand, right? So we're going to use the Belgian firm-to-firm network. We're going to see who's supplying whom, and use that information to back out who might be competing and who might be similar firms. And so for that, we're going to develop a tool which we call Firm Embeddings. And the idea is to generate the latent space in which firms, so firms are multi-dimensional objects, but this low-dimensional space, we're going to see which firms are similar to each other in this underlying space. And the idea is that if two firms have the same embeddings, they are probably going to be, two firms which are supplying to the same customers are going to be similar firms in that sense. That's kind of the intuition. Now that's great. You have a latent space. You would like to map this back to observables. So how well does this a model or algorithm do to map back to observables? The idea is that firms which are similar embeddings are substitutes and hence competitors. And we're going to map this against the dimensions that matter for competition policy or relevant market definition, geography, and product space. Geography, we find that firms which are close by in geographical space are similar in their embedding space, and those are potentially competitors, but there's a massive variance across sectors. So for some sectors, if you do this sector by sector, for some sectors, this distance matters a lot. We go back to the idea of ready-mix concrete as a very geographically split market. Other sectors, which are like finances or very large manufacturing, are nationwide competition. You see that also in those trade patterns and their embeddings. Product space, we're going to see a firm, what products do they produce, do they sell? And firms which produce similar products are also similar in this embedding space. So that's kind of, for now, a proof of concept that the model is actually able to recover those product and space characteristics. So this is early work, so I'm very much looking forward to any suggestions that you have on this. But so this is based on the word embedding. So these are the authors of the word2vec, but it's the most famous word embeddings component. This has been used for embeddings beyond words by Rudolph and co-authors. There is a shopper paper by Susan Atty and co-authors, actually, which is very close to what we're doing. The idea there being, I have a basket in the in the grocery store. Given what's in my basket, can I predict what's going to be the next item in this basket? If I see bolognese sauce in my basket, most probably I have in my basket, or I will have in my basket, pasta, right? That's kind of the idea. And then there is people that have been working on product representation, so using text descriptions of, for instance, products to see whether those products or firms are similar to each other. And so Hoburg Phillips has 2 papers in 2016 on this. Okay. So let me give you an idea of what firm embeddings is. I think some people know better than I do about how embeddings work, but let me just give the intuition and how we map from word embeddings to firm embeddings. Talk a little bit about what data we use, and then talk about our proof of concept results that we have right now. And feel free to interrupt me in the meantime. So, what are embeddings? There's many ways to think about this. I've been asking a lot of questions actually. So there's many ways to think about this, but one way is to say you have a high dimensional sparse, not even numerical space, and you would like to collapse this to a low dimensional dense continuous space. So it's a dimensional reduction technique. And the cool thing is it works really well on non-numeric data. So if you have cat and dog, you can use that information to go to a numerical representation of these things and then get the similarity of those words. And the idea being that similar observations, cats and dogs, or cats and kittens, are going to be close to each other in this low dimensional latent space. And then you're going to use this information to predict or to model the probability of every observation given the context in which it occurs, right? And so I'll give an example of word embeddings. You have a text, or you have a series of texts and books. The word cat shows up in those different texts. This will be surrounded by other words and sentences or around this. Given the context around these things, what's the probability that the word cat will arrive? Okay. And so some applications are, for instance, what are synonyms? So think of substitution, think of competition. Cat and kitten, you will probably not see them very often together, but as a substitute for each other in the same context. If you work on your phone, certainly the last few months and years, auto-completion, predicting the next word or even next words by now, that's kind of based on the embeddings types of algorithms. Recommendation systems, what's the next movie I should see? And some are really good, some are, if I see Netflix sometimes, I'm like, okay, maybe they don't know me really, really well, but that's kind of the idea. So to give an example, so you have text, and we would like to go from text to context. So the simplest way to think about it is, let's say you start from the first premise, supposed to say there's a bag of words. I'm going to look at a document, a text. I'm going to strip all the information of this, and I'm just going to count every time a particular word arrives in this document, right? So this is document 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. I'm going to count how many times the word complexity arrives in the first document, algorithm, entropy, and this for every word. And we're going to look at this for other documents as well. So what you can see is that in this case, in document 1 and document 4, complexity, algorithm, and entropy, they appear multiple times. So probably they are somehow related to each other. Document 5 might also be related, just doesn't have entropy in there, but it might be related to the other two documents. On the other hand, there are two other documents, 2 and 3, which have information about traffic and network and nothing about the other stuff that's in the other documents, so probably they're not related to each other in this case. Okay, simple. You just take all the words, count the amounts of time they arrive in the text, and then match this to other documents. However, whoops, sorry. You have 170,000 words in English. That's a large factor. If you think about a particular topic, there's much fewer documents than these words. So you run into the dimensionality problem, right? So you have not enough observations to be able to say something about the correlations or the probabilities in this case.
So I'm confused. Why we said there are fewer documents? You can look at all the media, factors,
Sure.
take all the media
Yeah.
You can
But
make the
if they are
documents large as you want.
if they are orthogonal to each other, then they're
How
not.
do you define if they're orthogonal? If you have
Agreed.
That's
Yeah.
defined.
Agreed.
So
Yeah.
I don't see the dimensionality problem unless you say, okay, I'm limited to a set of documents by some other constraint.
Yeah. Agreed. So one way out is to say we're going to have this high dimensional sparse information. I mean sparse in the sense that if you have 170,000 words in here as a vector, only a few of those will arrive in a particular document, right? To a low, dense, continuous dimension. And so let's take another example. There's a text, or there are different texts where there's cat, kitten, dog, houses. This gets mapped into a low dimensional space, the embedding space, which is then continuous. And the idea is that, well, cat and kitten are highly correlated in this because they are both feline. And so this is just an example because those are latent spaces. They are not defined by the user ex ante, but just to get an idea. Yes.
I think I'd like to answer this problem about the fact that you can take text from the internet. I think that the problem of dimensionality here is not the relative dimension, the number of words versus the number of texts, but just like the number of dimensions in general. So you end up with enormous space, and you don't want to be working in this enormous space. You kind of want to translate the vector which you construct based on the text into like a much smaller vector in this much smaller space. So it's purely about dimensionality reduction.
That I understand. I'm
Good,
totally
good.
outside this list, but there aren't these dictionaries that people use. I've seen more in video analysis than in the context of firms, which I'm
Yeah, so that's the contribution that we do. So we take this, what has been used for words, and we're going to apply this to economics.
Okay,
yeah.
It has been applied to economics in some way.
In
What
text,
firms do,
text,
or description of products.
Yeah.
But okay.
So let me show you in
Okay.
the next slide how we think about it in the context of firms. But just to get the idea of what an embedding does, so you have those words that arrive. So let's say cat and kitten are very correlated, as I mentioned, because they're both feline. On the other hand, it's not related to humanity because men and women, king and queen, they are highly correlated here and they're not. Right? And so you can map this from high dimension to low dimension and even to 2 dimensions. And the idea is that in this latent space, cat and kitten are close to each other. Dog is here, and the word houses is completely unrelated. Okay. Yeah.
I keep getting confused. What do you mean by dimension? I mean, if I have a matrix, that's a map. Right?
Yeah.
That's a map between 2 vector spaces.
Yeah.
So where are you referring to a dimension?
So
So now it's 7-dimensional, right?
yeah, so this is high dimensional. This is all the words that you can have. This is a potential space of 170,000 words. You map this to a low dimension, which is 7 dimensions in this case. Right? Okay. And then, which is this is a latent space.
Okay,
think of
you
this.
don't know the dimensions, right? Like I mean, here in this example, you don't know the dimensions.
But think of
Generally, you
PCA.
don't know them.
Think of PCA.
Okay, so you're doing a PCA.
No,
Yeah.
It's not. Think of
Similar
PCA.
to
Yeah.
PCA.
I mean, PCA, you orthogonalize the dimensions, which is not the case because you're willing to look at the correlations here. But
So you first like create a matrix in which you have each word as a vector, and then you do like a model that basically finds an embedding into a lower dimensional space, and it gives you this matrix of translation. But like what you want actually is the values of vectors of individual words after the translation.
So yeah, so start from this example again. Suppose that every document has a potential vector of 470,000 elements. You count the number of those. So either you do the bag of words or the one under comedy. That's information that you have in here, but you would like to map this to this lower dimension.
And you're just picking 7 at random, or how many?
So yeah, so what we do actually afterwards we set this at 50. So there's just the trade-off between computational expenses and the detail for now. Maybe there are better ways to do this, but we just picked something for now.
Remind us, the original word to back is 150 or 300.
Yeah, something between 50 and 300 roughly is the order of magnitude of dimensions.
And you can set the dimension, or you can do like a grid search, or like.
Well, ideally, you have some sort of threshold of some metric that
Yeah, so you
you
can
will use
do
to
like,
get the number of dimensions.
you can create a heuristic for
Yeah.
choosing the parameter based on a parameter to be chosen, or you can
Yeah.
write like another model that
Sure.
chooses it for you.
It's just, I mean, right now this is all proof of concept, so it's not fully optimized yet. But yeah, so
Yeah. Maybe I was just getting confused by the matrix representations. because,
okay,
It's words, then it's documents, now it's subspaces.
Yeah.
So I guess that confused me a little bit. But
okay.
I think we're
Good, so you have words and documents, they are in the context, and so you would map those
Well, the
co-occurrences.
documents are not a dimension, right? So when you're talking about dimensions, you're always talking about words.
No, I mean, there are multiple dimensions. You have the dimension of the words, you have the dimension of the text, you have the dimensions of the embedding space.
So initially, you have a word, so each word is a vector that you derive from the documents. So the size of the vector is the number of the documents.
Okay, so your vector space is the documents, and your words are the vectors.
Yes, and then you reduce that to the.
Well, we don't. I don't
So
want to
let's talk about it afterwards.
Let's move on.
Yeah, good.
Originally, for each word, you have 1, 0, 0, 1, or
Yeah.
a gazillion time because you're a gazillion
Yeah.
document.
Yeah.
At the end, you have just 7 values.
For every word. Exactly. So that's kind of the idea. And so we would like to bring this to firms, how they compete with each other. And so firms are, again, multidimensional objects. It's in a high dimensional space. So we can think about observables and unobservables. Observables are firm size, which can be expressed in sales, inputs, full-time equivalents, the number of products, the identity of products, the value of those products that you're producing, the location of your seat, and a bunch of unobservables, where it's also very important for us in many underlying econ models as primitives, right? So productivity is unobserved, was a key driving factor of firm heterogeneity. So either we're going to use that observable or proxy for unobservables information and then see how firms compete in those dimensions, or we're going to bring this to this latent low dimensional space. And we're going to do that using information about sales transactions between any two firms in the economy. So the idea is as follows. We're going to model every observation conditional on its context. So every observation is a firm, a supplier here, and its context is going to be all the other firms which are co-supplying the other customers. And we would like to predict the probability that any firm I is supplying any customer J in the economy based on the context in which they are operating. And the idea is that firm A is going to be similar to firm B if they tend to co-supply the same customers, right? And so graphically, this is saying we look at the probability of firm A, the blue guy here, supplying any other firm. And this context is going to be all the other blue guys in this case, because they both co-supply the two customers in this case. So those blue guys are going to be similar to each other. The red guy is only supplying the first customer. The yellow guy is only supplying the second customer. So they're not similar to the blue guys, and they're surely not similar to each other. That's the intuition. A little bit more formally, we will have a set of producers which are indexed by I running from 1 to n in the economy. There's going to be a sales relationship indexed by AIJ, whether you're supplying or not supplying a particular customer. That gives you a full square matrix of n by n. All firms as a supplier, all firms as a customer in the economy.
Ask you a couple of comments. Can you go back to?
Yeah.
So first of all, so you're gonna condition on what they're making, but we don't know what they're selling, you know?
No, we don't know what they're making. We're only saying, no, I
So
just
no,
give
we
you.
understand. So what do you know about, what do you know, what if they're selling completely different things? You don't care.
No, we just say,
So you say,
we only use whether there's an error or not.
but you
nothing
say they're
else.
competing. What if they're not competing? What if the buyer is buying completely different things? There's
So,
two
so
inputs in there.
that's exactly what we'd like to recover after mapping back to the observables.
Because like most firms wouldn't just supply to one person, right? So like if the idea is that later on, because of the size of the data set, you will see this similarities between the points that, and from that you recover what they actually sell and whether they're similar or not.
Because in principle, you know something about these firms, about what they're.
Yeah, but we're not going to give,
So
we're not, we're giving it the minimal information. I'm a firm, I'm selling to these guys. That's it.
And the other comment was about the fact you're saying this is the set of all producers, of course, that's a cheap comment, but it's too very important for Belgium. There's all, Belgium is not the whole, there's a lot of transaction with the rest of the world that we are also, that's gonna create some measurement error because there's competition with the French and the Dutch and all of these is not observed. I mean.
Yes, so that's why I was talking about.
The firm level trade data, the informational customs data, then you could think about how potentially.
Yeah, but then
you don't know the other side.
You cannot put it in, yes, that's why. So you cannot merge the two matrices because the dimensions are going to be different in that case.
Okay.
But fair point, and that's why I said regional and national in the beginning.
Yeah, no, I understand that. I was immediately thinking of the international, but you cannot.
No, not for now. But conceptually, it should be possible.
Yeah.
Yes.
So you also exclude the exports abroad, right?
Yeah.
So it's just local.
It's just
Okay.
domestic firm-to-firm sales.
Okay.
That's all. Sorry. It's not the full world.
And there's no geography that you're putting. You're simply putting
Nothing. It's what they call an edge list. So you have a firm I selling to firm J. That's all information.
And you're gonna try to infer.
I'll show you.
I'm just trying to see where you're going because
So
you started from
So what we would like
market, what's a relevant market? Is it Flanders? Is it Wallonia?
So,
is it what? I don't know.
I'll show you. So for geography is the clearest example. I just feed this information, and I can show you how segregated particular markets are. They're not for ready mixed concrete. You're only supplying to particular customers which are very close by because you need to empty your truck before it dries out, and which is less than 30 miles, right? So it's not a national market. There's no national competition in this sense. Other markets, like for financial industries, this distance doesn't really matter. So firms who can be similar in embedding space because they're serving national-wide actually, and so I'll show this difference across sectors. So with just giving information about who's co-supplying who, we can back out a lot of information the geography. I'll show you. And the same for product space. So back to the idea. So set of producers, whether or not it's a 0-1 adjacency matrix, and that's all the information you get. So we don't know which sector the firm is, what it's producing, the value of those trade flows. We're not even using it, right? So the minimum information you can use.
There is a question on the chat.
Are there two types of embeddings used? No. Sorry, so we're only going to use the embeddings of the supplier buyer matrix. No text information here. No. So the 10K filings is a Holbrook-Phillips kind of approach to things, but so we're not using that information. Good. So that's the information we have. We would like to understand what's the probability that firm I is going to selling to firm J. So it's going to be in the set of suppliers to firm J. Given the context, given all the other suppliers that are also selling to firm J. Okay. We're going to take the simplest model again. We're going to say it's Bernoulli distributed. And we're going to say, okay, now aggregating across all suppliers, we can say, what's the probability that a particular subset of firms are going to be supplying firm J? So out of all probabilities, I pick a subset. What's the probability that these guys are going to be supplying firm J? Aggregating again, you get actually kind of the probability of a particular network arising. You can aggregate over all customers, and so this is saying what's the probability of this exact adjacency matrix arriving. That's great. It's the simplest model you can do. It's not possible to take this to the data. Same problem. Of course, the dimensionality, you have only one estimate per data point. So there's no way to get information about the distribution or the probabilities. Enter embeddings. So the idea is to parameterize this conditional probability using this low dimensional continuous vector spaces. And so the idea is for every supplier I, you will have two vectors. One is a embeddings vector rho of dimension k, which you choose. In this case, we choose 250, and a context vector. So who you're co-supplying with, same latent space dimensions. And both of them together, depending on how you're going to put those two vectors together, are going to determine the joint probability of this arriving. We're going to again take the simplest way of putting those two vectors together in a linear model. So the vector, sorry, the embeddings vector and whatever is the other guy's context. So the embeddings vector plus all my other contexts as a supplier to other firms. And then we're going to map those model outcomes back to probabilities just using a link function. So think of like a logistic link function to go from model outcomes to well-defined probabilities. Okay, so that's the model. The probability of firm I selling to firm J, given the context of all the other guys selling to firm J, is this component. So that's the linear embeddings model with the link function. We also need to model the probability that you're not supplying to a particular customer, which is just 1 minus this thing. Easy. Problem is, if you have worked with large sparse matrices, I mean, 800,000 firms squared, 64 or 640 billion potential entries. 17 million exists in the data. The rest is all zeros. If you want to take this as a full, that's impossible, right? So what they do is it's random sampling with a very small subset of those. That's what they call negative sampling, in the sense that if you sample all those zeros, which are much smaller than the ones, it's computationally feasible to be able to calculate those zeros and ones probabilities. Okay. This gives you the objective function to back out the probabilities. So it's the log of this. It's a log of this thing. The probability, conditional probability that you're supplying this guy versus the probability you're not supplying those guys, and some regularization terms actually. So yeah, so also in this case, it's priors on the embeddings and context factors, which we're just going to use L2 regularization. And I think you can probably explain much better afterwards how and why they are used in this case. So that's how we do it. It's not maximum likelihood. It's not a log likelihood function. It's a loss function because it's not well defined, the probabilities otherwise. Get those vectors for all i's in the economy. You need to pick some parameters. So this embedding space I mentioned, we pick 50. We let the model run for 50,000 iterations. The negative sampling size is 100. Just to give you an idea about computational expenses, the first time we were able to run the model fully was on C++ code. It took 5.5 months. Yeah. Enter Yabra, who was starting his computer science PhD. He rewrote everything in JAX, and now it runs into 6 days. But still, I mean, we're not sure that we are in relevant tolerance territory to make sure that this thing is converging or not. But like the slope is at least the slope of the loss function not changing that much, so that's kind of where we stop for now. There are again better ways probably, but otherwise we have to wait until infinity to get some results.
What do you run it?
Sorry, it's just CPU, so not even GPU. Yeah, so it's JAX on traditional laptop with many CPUs server. Yeah. So if you know how to improve it, the problem is we're also constrained with the infrastructure of the National Bank of Belgium. Because so first, I mean, we have to run stuff on their server. First, I asked to install C++, and that had to pass 4 committees because it means they had to open the secure server to the internet to install this particular thing, which they could not just, I mean, you have to compile, so you could not just install it, and it took another 6 months. So just there's a lot of hoops that are not even related to the mechanics of this to jump through. Yeah. Yeah. So that's the idea. You're going to estimate probabilities of every link existing, given the Bernoulli assumptions and the linear embeddings. Now, we're going to take those factors of 50 dimensions for every firm I and every other firm J. We're going to see how similar they are in this embedding space, just using cosine similarity. Okay. And then this similarity of any two firms, we're going to see how much this matches with similarity in observable characteristics. That's the goal, and that's going to Paula's comment before, which is what we're going to do right now. So we're going to use the National Bank of Belgium B2B transaction data sets, which we developed with the National Bank almost 10 years ago now. And we're going to pick 1 year, 2014, and we're going to take all the transactions that we observe in the cross-section, which is 14 million links across all economic activities and regions. This data set contains information I'm selling to Francois for 700 euros. We're just going to use 0-1 information in this case. And then for other stuff, to match back to the observables, we're going to use firm annual accounts. So the sales, inputs, employment, labor costs, location of the firm, the main NACE code, capital. And then for industrial production, we're going to use ProdCom, which is at the 8-digit level. For every firm, we know what they're producing, the value of those quantities, etc. So from this information to this. Okay. Yes. Oh, sorry. Your approach is computationally based.
There's a sorry.
Okay, Thibault and Jeremy, yes.
My question was for later, so
okay,
feel free to continue with your reasoning.
Great. Yeah. So actually, on your comment, we are actually going to make the codes available so you can see whether or not it runs on your systems. Yeah. Good. Jeremy?
Hi, Glenn. Hi. Can you see me all right? I
Yes.
just turned on my video. So I've been working on embeddings myself in a different context, a bit like Shopper. And an advantage that I have with the grocery data is that if I just keep watching customers come into the store, I just keep seeing new contexts for each good, many new contexts. So I just so if two goods are different to each other in some meaningful way, then eventually it's going to show up because there'll be some reason to purchase them, which leads them to appear in some baskets differently to others. So I'll see that because these baskets keep being generated. So however subtle the difference between two goods may be, eventually they're going to show up in slightly different compositions of baskets in the aggregate. And another way of putting it is I have a large T asymptotic, so it's consistent. What I'd like to ask about this is that if you take any given firm in this network, then it might have 8, it might have 10 suppliers, might have 8 to 10 companies it's supplying to. So I seem to not really see, I don't have an asymptotic theory. Another way of putting it is I just don't see rich enough differentiating data over time because I just have the one network.
Yeah.
Which is just that. It's like as if I have only one observation, which is one network, and like I think Carolina was saying earlier, two companies could be completely different to each other, but just have in terms of what they sell, but just tend to happen to have the same customer network at a point in time. Yeah. If I saw repeated observations of those customers in fresh networks each time, then eventually I'd see them playing a different role in these networks.
Yeah, so very good point.
Yeah,
sorry.
Thanks. I think you get my point. Yeah. What's the asymptotic limit theory? In what way can you say this is consistent?
Good. Good question. I don't know at this stage. What we can do, this is all just proof of concept right now. But so right now we have 20 years of observation. So we could use the panel data of the firm transactions to see whether or not these things. It's just right now we're just turning the knobs to see what we can find, and if things are interesting enough, we can see if we can push this thing to a full-blown model and analysis. Yeah.
Even without going to the 20 years, within a year, you have all the transaction over during the year, no? It's not that they all.
No,
in
it's one observation per year. Yeah.
I
So
didn't realize all collapse.
yeah.
on the
So
yearly
it's
level.
the sum. So how it works is at the end of every calendar year, I as a firm has to report all of my business customers
I
and how
thought it
much they
was
sold.
monthly or something, but
No,
okay,
no,
fine.
no. But so very good point. So I fully agree. I don't know how these things work given the underlying structure of the data and the model. So I'm not sure. We should sit down to see how the asymptotics works in this case. But very good point. Yeah. So Jeremy, we should definitely talk afterwards about this. See if you can help. Thanks. Cool. All right. So another thing is actually that. Let's postpone it afterwards. So there's some cross-sectional variation, right? So you need non-full overlapping customer sets probably to identify stuff. It's like a fixed effect in that sense. But so let me show you what you get in the cross-section and then see if you agree, if you can show something or not. Good. Okay. So as said, we're going to retain only information 0, 1, whether you're not supplying or not a particular customer in a given year. And then keep all the information about the observables to match the embedding space to the observed space. We're going to drop firms which have only one supplier because those suppliers do not have a context. It's like an unidentified fixed effect in a sense. We're going to drop all transactions which are less than 1% of the input purchases baskets of the customer. It's ad hoc, but this drops the sample size by 50%. So I mean, the underlying idea is just to say, well, if I import and I buy sandwiches, it's not really going to be an import supplier to me in this sense, perhaps. I mean, so yeah. So we end up with 7.3 million transactions across 800,000 customers and 400 or almost 500,000 suppliers.
Sorry, I'm confused. When you say less than 1% in value or in
Yeah, so input share. So you look at the total expenditures of a customer, how much every guy is supplying to me, and I divided sales to my total purchases by guys. And if that's
I
one,
thought you were not using it all the value you said before.
yeah, no, but so this is just sample selection.
Oh, okay.
So for the algorithm, we only feed this. Yeah. So we're only going to feed those 1 zeros which are important enough in a sense.
There you're using the link, but to create a sample.
Yeah. It's ad hoc. Yeah. Good. And maybe going back to Jeremy's comment or question. So what's the average number of suppliers per customer? Around 9, and the median is 7. So we know there's a bunch of outliers in the right tail. We have some bite in the cross section, I hope.
Do you throw away like distribution?
No, nothing.
So you keep this as firm, so that this will be a distribution next, like delay.
I agree. I agree.
So these are not really making anything. They're just the Walmarts of Belgium. Does it make sense to keep them?
Good point. We haven't thought about it, but that's a good idea actually. Yeah. Okay. 15 minutes. So I'll end on time. Good. So we just have some proof of concept stuff. If you have ideas, feel free to let us know, because I mean, we have the machinery. It's more getting by to show that this thing works in product space and in geographical space. So what we're going to do is super simple stuff. We have this cosine similarity of the embedding space. We're going to look at any two firms, I and J, which are in the same NACE 4 sector. So they're both suppliers in this case. I should change the index. So firm I supplying any other firm, firm J supplying any other firm. They're both in the same NACE 4 industry. How does cosine similarity correlate with the distance between those two firms? Geographical distance. We do this sector by sector. So we have 430 NACE 4 sectors. For the vast majority of those sectors, cosine similarity correlates negatively with distance, which means that you need the interpretation in the sense that you need to be close to your customers to produce. If not, it means that I am one supplier, I have my own set of customers. I'm firm J, I have my other set of customers. We are very far apart from each other in geographical space, and we're not related to each other in terms of cosine similarity.
I'm a bit late in asking that. Why aren't you doing it the other way around? That we're similar if we're buying some stuff.
Yes, that's another. So I raised the question in the beginning to the team. You haven't explored that yet. If you can write it down the right way, I fully agree. Because so we don't have any theory right now to see what's the right way to do it. If you read the competition policy view or the legal documents for the European Union, it's very often they say there's 3 dimensions. It's geography, delineated geographical competition, and substitution, supply and demand substitution. Actually, so indeed those 2 components might. Yeah. Now the question is, do we really capture supply and demand substitution by modeling it this way? But that's not. Yeah. Owen.
Up there, shower thoughts. But I think there's something really cool about the structure that you have is so you have the supplier network and the customer network. And so each firm is a map from the space of firms to itself. And I think that is something you could possibly do something with. So because if you think about the suppliers capture some of what you're thinking about in terms of product space and in terms of the quality space as well.
Right.
And so you'd at least be keeping that information in there.
Yeah.
If you have some way of keeping that information, right? Because right now you're throwing away half of the information you have, right?
That's a good point. And so you're saying it's A transpose A or something like that, or
I think there's something cool.
Okay.
And each firm represents a map from firms to firms. And that just seems, it seems like there's something very structured.
Yeah. That's a good, So we can, yes. So, yes.
2 points. I don't fully agree that we need to looking at inputs of firms. There is more about competition than output. Because sometimes you want to look at the competition. Like, if for INET the substitutions between sandwiches and meat, the inputs of the 2 suppliers will be very different. But for us, it's going to be very important. And that's the first point. And the second is, so you look at the distance between the 2 suppliers. And you say that they tend to supply very different set of customers. But if you go back to the very simple theory of the beach shop, if you have a beach, the 2
hoteling,
and that means that they are very co-located, but they supply very different set of customers.
It depends.
They might.
Yeah, it's depending on the model that they're on the same place or they're on opposite sides of the beach.
Exactly.
Yeah.
That's not something you can say. Like
no.
The fact that they're very close or not close to each other doesn't say anything about very different set of customers. I don't know why you could say that.
No, so I mean, your embeddings factor is saying what's the probability I'm going to give to be supplying a particular guy. So suppose what's the probability I'm supplying Francois, given my other firms which are also co-supplying Francois and Paula. So I can derive a probability whether or not I'm supplying either you, and anyone else in the soup. Right? We're going to be very similar if we tend to supply to the same customers. That's a cosine similarity in a sense, right? If not, it just means that you're supplying other guys. Right? That's information you feed into the embeddings. That's the information you get back from the embeddings factor. So if they are not similar to each other, everyone's supplying someone. It's just that you're supplying other people. Right? So you're very similar. This cosine similarity should tend to the highest, I don't know how it's bounded, but the highest value, if you're both supplying exactly the same number of customers, the same customers, is going to be minimal if 2 suppliers are completely disjoint in their set of customers. Yes.
So I guess I'm wondering if you've also looked at other methods to do this, right? I mean, there's lots of alternatives. You pick one of them.
You mean instead of embeddings?
Yeah, I mean, let's say forecasting, who additional suppliers or customers.
Mhm.
I mean, we've heard yesterday that for the product basis on a national level, machine learning algorithms actually outperform relatedness measures. So I'm basically wondering, you know, why is this the best way to do it?
So we talked about it at dinner actually yesterday evening, and so embeddings are very close to actually boost in this sense. I think we started with the ideas of using embeddings. I mean, the biggest problem is really like it's from independent probabilities to dependent probabilities, right? So you need to, that's the way to go with it. That's where we stand right now.
I think a valid point would be to compare the probabilities you're getting in the embedding space to the probabilities of just perturbating the network, right? Because you derive the context from the network, and then you basically put like advanced NLP to get the probabilities. But if you get very similar probabilities from just like putting some kind of randomness into the network that you're given, then the cost of using the NLP is not justified. But I do believe that you might recover much deeper information from this, right? Because it's not focusing just on geography or the type of product, right?
I mean, so the goal of this exercise is not maximum prediction, because we are taking the simplest model, stripping everything, right? I mean, so we're just feeding information 0, 1. We could use a value, we could go to Poisson distribution, we could go to much more complex embeddings and improve on prediction power probably. So this is just a proof of concept, simplest thing, toy model. What can we do? And I mean, we didn't feed anything in terms of, and let me show you the example that I had in mind. So sorry.
The R square of these things is.
I don't know. This is sector by sector, right?
Yeah.
So you have an R square for every sector. So I don't know. Good question. Yes. From the top of my head, I would expect 5 to 10%. If you do this kind of firm level regressions without any covariates, it's this order of magnitude mostly. Yeah. But let me show you a case study after this. So this is like sector by sector. For most sectors, this distance matters. And if you look at the identity of the sectors and you rank them from most important distance versus not, this kind of lines up with our intuition, right? So if you're in wholesale of intermediate products, in landscaping activities, ready-mix concrete, support activities of crop production, you need to be close to your, I mean, the correlation between similarity and negative distance is going to be much higher, right? So we didn't feed this information to the algorithm, right? Other stuff, activities of call centers, financial leasing. Yeah, so those are the easiest examples. Distance doesn't really matter. Seems to be some competition at the national level in this case. Okay. Even a nicer case study.
Can you go back just one
Yes.
second?
So for those sectors, the distance is mostly negative correlated to the similarity, which means that if you're further away, you're not co-supplying the same customers.
Is there other characteristics of these sectors that would, like there are all these measures of like face-to-faceness in the there, like could
You could,
really
I mean,
like
so,
to say, okay, does it make sense? I mean, we are eyeballing a list that is, you could see.
you could, I mean,
If
let
we
me show
like
you.
to validate them
Yeah.
vis-a-vis other people.
So this is our validation exercise.
Okay.
We're going to look at one sector.
Oh yeah, you're gonna do the cement
Yeah,
or something.
exactly. Everyone knows.
Yeah.
This is clear. We know it's an homogeneous market. We know how it works. We agree how competition works there. We see if we can recover this market or not. So Sivers in 2008 started his career with this paper. Perhaps no other manufacturing industry faces greater transport barriers, right? So the idea is that if you start filling your truck with ready-mix concrete, you have to ship it off and empty your truck before it gets hard. And this is roughly 30 to 50 kilometers. And then you're stuck with a full truck of hard cement, so you don't do that. So that's the very geographical market, right? Very localized market. It's not nationwide, it's a set of quasi-independent local geographical markets. And the average shipment distance is 32 miles versus 550 miles in the US for all other commodities, right? So this is a very clear example of how regionalized a particular market might be, and competition might be across cement suppliers in this case. So what we're going to do is we're going to take the cleanest example possible. We're going to look at all ready-mix concrete suppliers in this NACE code. We're going to only look at single product suppliers of ready-mix concrete and single establishment firms. So there's nothing else that's driving the underlying results. We end up at 69 single establishment, single product ready-mix concrete suppliers. We look at their embeddings, and then we're going to cluster them using a k-means clustering algorithm with 3 clusters. You can do this 2, 3, 5, whatever you want. And this is amazing. So this is Belgium, which is not so amazing, but this is Flanders, the yellow. This is Wallonia, the red parts. This is Brussels. And these are all the establishments or the single suppliers of ready-mix concrete. And the dots, the colors, are the clusters in which they are attributed to.
So Brussels is very.
Yes, they speak the same language. Wallonia is one cluster. All the firms of Wallonia are co-located or allocated to the same cluster. There are 2 clusters. If you do this, 2 clusters or 3 clusters, so if there are 2 clusters in Flanders, which are completely geographically segregated. So those firms are much closer to each other in the embedding space than those firms and those firms.
You see, it's not only distance, it's geographic, no, language.
Language
distance.
matters as well. And so even here, I mean, this is very funny because Steven was like, what's the difference between those 2 clusters? I mean, here's the Schelde, which is the river. And it's very funny, from a very old, long perspective, it's those 2 provinces which tend to work together in anything business related, and those 2 provinces. There's no spillover across those provinces by accident of having a river in between. So this is, I mean, you just feed in whether or not you're co-supplying other firms or not, and you get this geographical and even underlying language component and cultural component that matters in this case. So I think it's pretty powerful. We also do an exercise.
I have a
Sorry.
quick question about which is totally unrelated, but the secret something made me think about. So do we know anything about ownership? I mean, to be a dot, you have to be a VAT number, but do we know that maybe one owns another ownership linkage?
No, so these are, I mean, in general, no. For this exercise, we stripped all of the information. You're a single establishment, single product firm.
But
so this is not, it's not CMEX, it's not CMEX,
okay.
right? So, yeah.
Right,
Yes, Owen.
okay.
Yeah.
And it would be nice to have a scale on the map, because we have the radius for each firm, right?
Right, so yeah, so Belgium is small, this is 200 kilometers.
Okay.
Yeah. Even in Belgium, distance matters, right? So, yeah, good. Last exercise, we want to do something similar. I'm very much looking forward to your feedback because it's kind of not conclusive right now. But so we're going to look at multi-product firms, what products they produce using 8-digit products, and see how they are similar in those product spaces and their embedding spaces. So just to give an example for people who have not been using this kind of data. So this is 8 digits, 24, 20, 12, 10, and 50 are very close but different products. They're both casing, tubing, and drill pipe of the kind used in the drilling for oil or gas. Seamless, one is of stainless steel, the other one is other steel which is not stainless. Same, other 2 products in textile. Woven fabrics of cotton, not of yarns of different colors. For clothing, one less than 200 grams per square meter density, the other one above that. So that's a level of detail that you can compare products. What we're going to do is we're going to look at firms. We're going to have 2 exercises. First, we're going to think of a firm, its products as a bag of products. So we're going to count how many products or like 100 counting of products, and we see whether 2 firms which produce the same amount and the same products, whether they are similar in embedding space or not. And the other exercise is going back to the Holberg-Phillips idea. We're going to use a text description here. These things, we're going to do text embeddings on those and see how they correlate with their firm embeddings. They are positively correlated in the product space and the embedding space, both continuous and in rank order. It's just that those values are not extreme. I mean, they're super significant, of course, because you have many observations, but we would like to see higher numbers. Long story short. But again, we're not feeding any other information in this case, right? So.
But what do we take from this? Are they competing if they're more correlated, or maybe they are indeed, these things are different inputs that are complementary? So, I mean, if we go back to the question, is this a market? Because, you know, I don't know, I'm trying to see
So,
also from the antitrust.
Yeah, so for now, it's really about similarity, whether two
Yeah.
firms are similar or not. And our interpretation for now is mostly that you are competing if you're very similar, because you're serving the same customers, right? If I am, without knowing the information of the content of the transaction, if you and I are both serving this full room, we are probably competing for the demand of those guys. There's ways to think about complementarities as well, so we can expand this in other dimensions, but yeah, that's it for now. So let me conclude a little bit over time. So defining relevant markets is key in many applications, both in micro and macro. Once we start calculating market shares, we're stuck. How to think about this? We develop a methodology which we call firm embeddings to define those relevant markets, in which firms are similar in a particular latent space. And then we try to back out again whether firms which are similar in latent space, whether this maps back to similarity in observables. And so we look at geography and product space. And so let's call it similarity rather than competition for now, but so we should push the dimension of the project that way.